Thank you. Hi, everyone. I'm Zalim. I'm writing Kotlin in Kotlin at JetBrains and leading Kotlin Wasm. We are going to have a quick journey around Kotlin Wasm, and we will see what kind of things already possible, and then also look a bit inside.
Hey, I'm Sébastien Deleuze. I'm working at VMware as a Spring Framework committer. Today, I'm not here to talk about Spring, but if you want to chat about running Spring on Wasm, you can talk with me. I have a few ideas. But today, we are really going to talk about Kotlin Wasm and the work I do on that on my spare time in collaboration with the Kotlin Wasm team. So first, a quick presentation of what Kotlin is. Kotlin is a modern statically typed, garbage-collected language. It managed to be both concise and expressive, pragmatic but elegant. And in my opinion, I found the right trade-off between imperative and functional programming. It manages to turn the billion-dollar mistake, null references, into a pretty useful feature of null safety check at build time to detect the presence or not of a value. Main adoption is on mobile side because Kotlin, as you may know, is the official language on Android side. We have a fair amount of market share also on server side, especially a lot of people are using Kotlin to build Spring Boot application. And thanks to its DSL and scripting capabilities, we are basically able to use Kotlin to write Gradle build files. Most of the successful use cases are on JVM, but Kotlin provides a pretty first-class support for multi-platform development. So basically, you write your common code in Kotlin, no dependency on a specific platform, and you just write the specific bits for the JVM, for native, for JS, and that's it. The JVM is mainly, the tooling is mainly JVM-based, and there is a pretty powerful compiler plugin mechanism that allows to perform code transformation at build time. So about Wasm, I would like to share a bit of history. So since I work in this industry, I try to find ways to remove text silos, to be able to use the same code for various use cases. And so in 2016, when WebAssembly was in a process of being standardized, I shared this crazy idea with the Kotlin team and the Kotlin community about targeting WebAssembly for Kotlin. At that time, that sounded a bit crazy, but since I have been dreaming of a dedicated support for Wasm in Kotlin, and that's what we are going to show today. So first, it has started as a prototype where Kotlin native, which is a version of Kotlin that generates a native executable using an LLVM toolchain, was a bit modified to generate WebAssembly. But what we are going to present today is a brand new compiler that is natively designed for targeting Wasm GC. We had a good presentation by Google about that and by Kevin about that. So yeah, Kotlin Wasm was born to really target Wasm GC, and Zalim, who has worked on the compiler, is going to present you that. A key point about Kotlin Wasm is that it targets a competitive footprint, including for public websites. So we have already talked about using Wasm GC to draw an interface with basically a library that is 1 megabyte, for example. But here, we also would like to target public websites. And this pretty efficient compilation is illustrated by this 3 kilobytes footprint for a very simple Hello World application like that basically uses the DOM binding. But that means that Kotlin Wasm is also usable to target public websites, not just back offices and stuff like that. Zalim, you want to talk more about the new compiler plugin?
Thank you, Seb. We built new compiler from scratch and targeting next goals. We want to have fast compilation because we think it's important to have under the second time, round trip time. To achieve this, we generate binaries directly, and later we're going to make it incremental. We don't do much optimization during development, but we use binarian to optimize release builds. Also, we want to have small binaries and great integration with hosts. For example, to avoid leaks with cross-model links. And modern shiny proposals help us a lot with it. We are using next proposals. Reference types which introduces basic reference types and instructions to work with them. It's already part of core specification and implemented by most of VMs. Next is exception handling proposal. As you can guess, it introduces something like exceptions, some ways to throw and catch them. It's in phase 3 or 4, but it's available by default in all major browsers. Next, type function references. The name speaks for itself. It adds better typing for functional references and instructions to call functions through a reference. It's in phase 3 now. And last but not least, garbage collection proposal. Interestingly, the proposal has only one sentence about garbage collection, but it introduced high-level concepts required for languages and runtimes with GC, such as structure, fields, references, and so on, also in phase 3. We have a great news today. Origin trail for Wasm GC in Chrome is open for registration starting today. It allows you to turn on Wasm GC for your site. Follow the link for more information. WebAssembly evolves continuously, and there are many new proposals. Some of them are interesting to us, and even more, we are experimenting with some of them. Let's quickly look at them. There are many proposals aimed to improve interop with external world. Performance is important as well. You can say nowadays disk space is cheap and networks are fast, but there are use cases where size is still important. For example, web. I'd like to highlight a few proposals here. First, component model, because I personally think it is important for whole Wasm ecosystem. Next is multiple memory, because it can unblock some interop cases, for example, between models compiled by different languages. And last one is Stringref proposal. I'll explain it a bit later. Let's take a deep look at some Kotlin Wasm implementation details. We start from Kotlin Any. It's a base type for everything in Kotlin, something like Java Lang object, but better. From the Kotlin developer point of view, it's only 3 functions and no fields. But actually, in terms of Wasm, it is structure with 4 fields, so every instance of any has these 4 fields. The table field refers on the table structure for the specific class. Now it is any's the table. All instances of any shares one instance of the table structure with references to the specific function implementations. The table, virtual table used for dispatch virtual calls, as you can guess. Let's introduce another class foo, which extends any with one more field. In Wasm, we extend any structure, repeat fields from any, and introduce the new one. We also want to change some method and add a new one. To achieve that, we introduce a new virtual table and change the type of origin of the table. Origin of the table field to a more specific one to avoid casts when we try to call some function. In the new table, we change the referencing for toString and introduce a new field bar for new method. OK, how to access fields and call methods now? Accessing fields is simple. Say we have a local variable d referencing on instance foo. We have a stack for values and instructions to execute. First, we need to put reference to the stack using local get instruction. And then we use struct get to access the field. It takes reference from the stack, read the field, and put value to the stack. Easy. To do a virtual call, we need a bit more. We have the same variable d with instance of foo, and now we want to call the method bar. Let's do that. We first put d on the stack 2 times. The first is an argument of the method, and second, we will use to reach the method. Next, we read the table field from the instance, and then read bar from the table, and finally, we can call it and see result on the stack. For comparison, a static call of function we know at compile time, it is only one instruction. Of course, if a function has some parameters, we also need to put arguments on the stack before call it. Kotlin also has concept of interfaces, and it's much trickier. Let's say the same class foo is implementing interface timer, logger, and maybe something else. So we introduce a new structure, itable1, with fields for each implemented interface. For each interface, we have a separate structure similar to the table with references to actual implementations. And calling interface methods is similar to virtual one, what we've seen before, but needs some slightly more instructions. Here is comparison of different calls. It gives a good sense of cost of calls, but be careful. It doesn't necessarily mean, for example, what every virtual call is five times slower than every static call. There are many aspects what could affect your runtime performance. Let's move to string internals. Most real-world applications work with strings a lot. So string implementation may have a big influence on the performance and memory usage of your application. At the start, we had some simple naive implementation, which is just wrapper over array of chars, and it is good both in terms of memory and memory footprint and performance, except one thing is concatenation. It is a proper operation of the strings. Doing concatenation over default strings, especially in hot path, is considered bad practice in many languages. And these languages usually have something like string builder in Kotlin. Anyway, writing concatenation is much simpler, and it is easy to underestimate the hotness of your code. So to optimize this case, we changed a string representation by adding optional reference to prefix and length. Assume we have 2 strings, Wasm and IO. If we concatenate them, we will get an object referring to the left string and share the array with right one. It could be chained like this until we fold it. It's fold on demand on all other operations. Now it is good on concatenations. In the future, we can consider improving built-in string for other cases, but there is a better option. It is Stringref proposal. The preliminary results of our experiments are promising: 60 times faster in interop micro-benchmarks and up to 3 times faster on DB monster benchmark. What do you see? It works a lot with DOM. Let's move out and look at what is already possible to do with Kotlin Wasm and the exciting opportunities there are. It is Jetpack Compose, the declarative UI toolkit in Kotlin, developed by Google for Android. Some time ago, a team in JetBrains took it and make it multi-platform and available on desktop, for example. So now you can write multi-platform application and use Compose for UI by writing code like on this slide. And now, it now works with Kotlin Wasm. It is demo. It is demo, originally built for desktop, but run inside the browser. You can follow the link on the top and play with live demo. It works perfectly in Chrome and Firefox. Even more, you can debug it other Kotlin sources, inspect local variables, and call stack very soon. Now, it's your turn, Seb, to show something cool.
Thanks. Pretty excited about the debugging story. So yeah, that's super exciting. Currently, Kotlin Wasm mostly targets the browser, and I'm a server-side guy. I also like to do front-end development, so I would like to explore what could be done by Kotlin Wasm for other kind of workloads. So earlier this year, I took the decision to create a new project, and this new project is KoWasm. The goal of KoWasm is basically to explore server-side and full-stack development with Kotlin and WebAssembly by leveraging Wasm for interacting with the system and component model in order to implement the interoperability. The vision behind KoWasm is just limited to Kotlin. It's a kind of opinionated anticipation of what could be the WebAssembly ecosystem in the future. The idea is that Wasm GC is going to change a bit the landscape. So sure, people will continue to use Rust and other languages to create nice and super performant applications. But I think there will be a lot of people that will begin to use languages that target Wasm GC, like Kotlin, Dart, Java, to write code that will run in the browser or on server side, sharing the business logic. And that's pretty exciting. Component model will likely be used to interact with the libraries and the various components that are written in different languages. And here, I think that we need languages that are closer to the metal, that have no or very little runtimes, and that's where, in my opinion, Rust, Zig, C, and C++ will dominate to write super fast components with a very tiny footprint, and those components will be exposed via WARG repositories, which will be close to what you have with NPM, with the JavaScript ecosystem, or Maven Central in the JVM world, to basically publish the various components. Maybe with WARG and WebAssembly that will be more decentralized, but the idea is really to expose some components that will be consumed by other languages. So I have begun to create this KoWasm library that provide and document various libraries. You can follow the link to check the documentation generated for Kotlin. The first package is Wasm, so the goal is to provide for now on library side some facilities to deal with the file system, environment variable, random number generation, etc. Ultimately, I hope Zalim and his team will integrate that natively in Kotlin Wasm, but for now, I explore that on library side. And since I am a Spring guy, I work on web servers, etc., I have begun to basically introduce some Kotlin API that I'm going to demonstrate to create a web server, define HTTP routes, and begin to build web application. A web client will follow in the upcoming weeks. That's interesting to see that I only needed a very small API surface from the Kotlin Wasm team to basically bridge the Wasm GC world with the linear memory. So the Kotlin team has provided to me a memory allocator that basically allow me to bridge these two worlds. And Kotlin Wasm also provides the capability to import some Wasm function, and that allow me to import the Wasm Preview 1 ABI and directly bridge it to expose that in a higher level Kotlin API. So if the network gods are with us, yes, that works. So here is what looks like creating a new server-side application with Kotlin. So you are declaring the Wasm platform, you are declaring a set of dependencies for KoWasm, and we are also leveraging the Wasm version of Kotlin platform libraries that we are using for data validation, like here. So I'm creating my data class user, I'm defining some validation rules that will be used on backend or frontend or where I want. I'm creating this fake user service repository that implements findAll and findOne method. And then I just begin to write my server-side application, creating an instance of this user service. I'm then going to create this web server. I could specify the port, the host. Here, I'm just going to define with the router DSL various HTTP predicates that will match. So here, we want that match for a text HTML media type. We can define some endpoints with get, post, put, patch, etc. Here, we are just going to do a simple get at the roots. It will return an HTTP response with the OK status code. And we are going to create a body with a method that will basically create the HTML content using a Kotlin DSL. providing full autocomplete. So here, I'm building my HTML like that. So this is regular Kotlin code. We don't have macros. We have DSLs where we can mix a pretty declarative approach with some real Kotlin statement like users.forEach, and then I'm going to iterate on each list element to provide, thanks to Kotlin interpolation, the user age, etc. This code, I'm currently using it on server side, but I could use exactly the same code on front end or wherever I want. So here I have my function that generates a string with the HTML body. I'm just calling it on user-service.findAll, and that's it. Obviously, I can create values over endpoint. I could do nested request predicates. I could expose the static resources that are in a directory. Yeah, we have pretty good capabilities there. The little trick is that for now, I'm using Node.js API to expose that because we don't have yet a standalone WASI runtime that provides both Wasm GC support and WASI support. So for now, I'm basically starting Node.js. I compile my Kotlin project to Wasm, and then I run it with Node.js, and that's it. So let's focus a bit more on the deployment side of the story, because this is pretty important. For now, I do a little trick, like I said. I'm using Node.js and Node.js API for the socket part because not yet available, but we are working to introduce Wasm GC support into the various WASI runtimes, like Wasm Edge, Wasm Time, and that will be the case. When that will be the case, we are going to be able to deploy that as a pure WASI workload without any JavaScript involved. We can ship that to Docker, to any Kubernetes platform, or to cloud or edge platform that support Wasm and WASI. So the goal is really to deploy a very small, like, let's say it will be 200 kilobytes web application instead of a 100 megabytes container that you have typically currently with enterprise solution. Another area where we do some work in collaboration with the Kotlin team is to understand how the WIT format, which is powering the WebAssembly component model, translates to Kotlin. And so far, this is a pretty good match. For example, we have WIT records that translate pretty nicely to Kotlin data classes. We can even use WIT option that translate to Kotlin null safety. We don't even need a wrapper on Kotlin side to deal with the presence or not of a value, and we have sound null safety at build time. Kotlin is a pretty rich language, and maybe some people will complain if I say that, but there is a lot of common points between Rust and Kotlin in terms of rich constructs and modern language capabilities, even if Rust is obviously not garbage collected. So here we can translate WIT variants to Kotlin sealed interfaces and classes. So that's a pretty straightforward translation. Sometimes the translation is more involved. The goal is to have a more Kotlin idiomatic code. So we are translating WIT results into Kotlin exceptions. So here we are doing a bit more involved translation, but the goal here is to provide an idiomatic API to Kotlin developers. Now let's go back a little bit on the front end. We have seen the nice demo that Zalim has shared about being able to basically, you have your Compose application for mobile. You can basically, without doing anything, have it on desktop and render it in the browser in a canvas. But like I said, I'm a web developer, so Canvas could be a good solution for back offices, for example, where I don't care to have 2 megabytes of Wasm to render the rendering engine. But myself, I want to be able to use WebAssembly and Kotlin everywhere, including for public websites. So I know people are a bit skeptic about that, but it's possible to use components that are basically targeting the DOM. So here we are using components like button, text, div, li, etc., in order to be able to leverage Compose capability to create reactive GUI that will automatically update where you modify the data. And the silly idea I would like to explore in collaboration with the Kotlin team is, if they agree on this journey, is basically take these Compose components where you describe your HTML interface. So here really we target the DOM, not the canvas. The goal is to try to, via a Kotlin compiler plugin, split the server-side code from the client-side code. So server-side, we are just generating the initial rendering of the HTML. It's a bit like the recent JavaScript and Jamstack solution are basically going more and more server-side and just doing the tiny bits of resumability on front-end. And so here we would like to leverage the powerful compiler plugin mechanism that there is in Kotlin to just extract the binders and the code that is inside the Lambda, translate that to Wasm, and only ship the teeny bit of infrastructure that will allow to resume the rendering, recreating the state on client side, and basically have a very teeny footprint. All of that should be invisible for the developer. The goal would be to develop server-side rendering, a site generator. I think the goal is to go from pure server-side rendering to pure front-end rendering and address the continuum of use case there is between via just pure configuration. That's just an idea that may be not possible. I'm not sure, but I would like to experiment on that. So what's next? I think the general availability of Wasm GC without a flag, because if you try the current demos of Kotlin Wasm without enabling the Wasm GC support in your browser, that won't work. Thanks to Origin Trial, we can begin to basically, make that work on Chrome for your website. I hope Wasm GC will be available in your browser without a flag soon. And I think that will happen soon. On Kotlin Wasm side, footprint improvements are already planned in Kotlin 1.9. So the 3 kilobytes footprint I shared, it's with basically internal builds of Kotlin 1.9. So we need to work, you need to work on that to make that possible. Compose for the web is really one of the first libraries that will take advantage of Kotlin Wasm capabilities. And I really believe this is the right platform for Compose and a lot of potential there. Currently, Kotlin Wasm targets a bit the JavaScript ecosystem. So I think there will be some evolution to be able to target pure standalone runtime with WASI, like Wasm Time, Wasm Edge, without any JavaScript involved. So you have a bit of work on that too. And currently, Kotlin Wasm is experimental. And I work on that every day. It's experimental. So it needs to mature a bit to reach the alpha status. On KoWasm side, so the framework I'm beginning to build, the .1 release is expected in May. So this is the point where you could begin to write some shiny web app with the API I expose. I plan to work on component model, maybe contributing Kotlin Wasm support in WIT Gen, the project of the bytecode alliance, but we need Wasm GC support in Wasm time, I think, for that. Switch to WASI Preview 2 when that's possible, and explore. So the idea I shared is a bit ambitious, so I think I would like to begin by exploring using Compose for web on pure server side, and then trying to do the clever compiler plugin stuff later. Thanks a lot. You can learn more about Kotlin Wasm in this link, and Zalim and me are available to answer to your questions. Thanks. Any question? Don't be shy. Yeah.
Thank you. Great presentation. You're talking about how to bring Kotlin to Wasm. Can you compare this to the efforts to bring Java to WebAssembly as well? If you see this as like a step towards that goal, or something that can be done in parallel, and how much of the work that you're doing could be potentially reused to Java or independent efforts?
Yeah, so Kotlin has made a bet on Wasm GC a few years ago, so they are moving forward. And maybe also it's also in terms of culture, I think that maybe it could go faster on Kotlin side, but that's true that on Java side, there is two main possibilities to compile Java code to Wasm. The first one is GraalVM. So I have been working on GraalVM to compile Java workload to native executables the past 4 years. Technically, it's possible to use the LLVM toolchain to generate Wasm bytecode instead of a native executable. I don't think this work has started already, but it's technically possible. The other possibility is via G2CL, which is basically the successor of JWT, and that basically historically compiled Java bytecode to JavaScript. Google is working for several years now to use that to compile, to generate Wasm GC, and it's working for simple example, but no reflection supported, etc. So here, it's super efficient, but you can't support advanced features. So I guess LLVM would be the way to support Java for server side, and G2CL could be a way to produce very efficient Wasm GC bytecode for the front end, and maybe it could be a nice idea to combine both.
I'd highlight one thing here. We, JetBrains, as tooling company, we focused more on tooling. We want to provide best tooling for debugging, for editing, and so on. And it's maybe one thing what is make special Kotlin in this area. Thank you.
OK, thank you.
Okay.